Hello dear students, Namaste. How are you all? Hope all of you are well. Actually, in the previous video, Thermodynamics Lecture 2, we have already discussed about the applications of work in the system and how the volume changes. As you can see on the top of the board, as I have written also, you can see W is equal to minus P external dV from Vi to Vf. Means how the pressure changes. About that already I have described you in the previous video, and I had given you the P external formula. Means whenever you apply a pressure in any system, how the work is done on the system and what the things are changes from volume initial to volume final and the pressure exerted with respect of volume. So you can see in this work done reversible, as already we have discussed about the reversible process and irreversible process. So W is equal to minus V initial to V final integration P external dV. A process or change is said to be irreversible if a change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that the system and the surrounding are always in near equilibrium with each other. Processes other than the reversible process are known as irreversible changes. See, already we have discussed about the reversible and irreversible changes, how this reversible and irreversible frictionless piston, as I have shown you in the cylinder also, that how we are applying these all the things, right? So you can see here that how this reversible and irreversible changes as we compare about the P external, pressure external, which was internal, plus dP, means it is a small change, and when you multiply dP by dV, it is a very small, very small. So you can write work reversible is equal to P internal into dV. As you can see on the board that already I have written that dP into dV is very small, right? As you can see, yeah. So now work done is equal to, if you compare, these are all the things already we have discussed. In the ideal gas equation, PV is equal to nRT. So P is equal to nRT by V, right? P is equal to nRT by V. So instead of P, what we are writing, as we have seen in the work reversible, we have got an equation minus integration V initial to V final, P internal dV, right? So instead of P, what we are writing, nRT dV by V. Okay? So nRT ln dV by V, that is equal to minus 2.303 nRT log V final by V initial. So these are all the things I hope all of you have known in the previous video only. In this video, we will go through a new term, but before that let me complete that what things we have studied in the previous video. We have also studied about the free expansion of a gas in vacuum, which is called a free expansion. There is no work done during the free expansion of an ideal gas, whether the process is reversible or irreversible. And we have written that work is equal to minus P external into delta V. So delta U is equal to Q minus P external delta V. And if a process is carried out at a constant volume, when delta V is equal to 0, so that time delta U is equal to QV. Yes. Now for isothermal and free expansion of an ideal gases, as we have seen that delta U is equal to Q plus W. For isothermal irreversible changes, Q is equal to minus W is equal to P external Vf minus Vi. You can see here in this changes, right? For isothermal, Q is equal to minus W, P external, volume final minus volume initial, Q is equal to minus W, nRT ln Vf by Vi, that is also equal to 2.303 nRT log Vf by Vi. For adiabatic changes, delta U is equal to adiabatic. Till that we have already studied in the previous video, right? And in this today new video, means lecture 3, is especially about, if anybody will ask you, lecture 3 is about what? It is about a new state function. In the previous video we have studied about the functions like pressure, volume and temperature. But in this video we are going to understand a new function called enthalpy, which is also denoted by capital H. We know that the heat absorbed at constant volume is equal to the change in internal energy. Definitely, you know very well, in any system, if heat is absorbed at a constant volume, remember that word, constant volume. Okay, so if a heat is observed at a constant volume, what will happen? Internal energy will change. So what will happen? You can see, as I have written on the board, delta U is equal to QV. What is the meaning of this QV, you know? Means internal energy has been changed as heat is absorbed in the system at constant volume. So that's why delta U is equal to QV. But most of the chemical reactions are carried out not at constant volume, but in the flask or test tubes under the constant atmospheric pressure. We need to define the another state function which may be suitable under this condition. First of all, as this new state function, which is also known as enthalpy, denoted by capital H, you must remember what is this new enthalpy. As I have already told you about the new enthalpy, that when a system absorbs heat at constant volume, then there is a change in internal energy, that is delta U is equal to QV, right? But here if we take this delta U is equal to QV, now if we take these things under the constant pressure, so delta U is equal to QP minus P delta V. What will happen? Delta U is equal to QP minus P delta V. You can ask me, sir, why these things happen? Because you know very well, where QP is heat absorbed by the system and minus P delta V represent the expansion work done by the system. See, whenever you will apply a pressure, it will be related to the volume. Okay? So at the constant pressure, when the heat is absorbed by the system, the work will expand by the system. So that's why I have written here delta U is equal to QP minus P delta V. Now just you comparison the equation first and equation second. Delta U is equal to QV and delta U is equal to QP minus P delta V. So if you represent these things in both the equation, what will happen? Can you tell me? I hope you know very well. See, delta U is equal to QP minus P delta V. Instead of delta U, you can write U2 minus U1. Can we write or not? Definitely, na? Internal change energy is changing. So for that we can write U2 minus U1. And QP minus P delta V. Instead of delta V, can we write V2 minus V1? Yes, definitely. See, instead of delta U, what I have done? I have written U2 minus U1. And instead of delta V, I have written V2 minus V1. Now I have rearranged the equation. What I have done? I have rearranged the equation. Means U2 minus U1 is equal to QP minus PV2 plus PV1. So what will happen? QP is equal to U2 plus PV2 minus U1 plus PV1. Now here, the another thermodynamic functions called enthalpy, denoted by capital H, came from the Greek word enthalpion. Enthalpion, to warm or heat, as H is equal to Q plus PV. H is equal to Q plus PV. Now you can ask me, sir, what is this H is equal to Q plus PV? You can see in the corner of the board as I have written H is equal to H is equal to U plus PV. What is U? Internal energy, PV, pressure volume, and H, enthalpy. So the work functions, new work function called enthalpy. Enthalpy is equal to internal energy plus PV. So the equation, if you put that equation, QP is equal to U2 plus PV2 minus U1 plus PV1. So here H is equal to U plus P delta V. What will be the value? U plus P delta V. As you can see, as I have written also, H is equal to U plus P delta V. Now, what will be the value of QP? Instead of QP, you can write H2 minus H1, that is delta H. Although Q is a path dependent function. What is Q? It is a path dependent function. And what is H? H is a state function because it depends upon the internal energy, pressure and volume, all of which are state functions. Therefore, delta H is independent of path. Hence, QP is also independent of path. For infinite changes at constant pressure, we can write the equation delta H is equal to delta U plus P delta V. You can see on the right side, from the bottom side, you can see as I have written on the last line, H is equal to U plus P delta V. QP is equal to H2 minus H1, that is delta H, and delta H is equal to delta U plus P delta V. Have you seen? It is very, very important to know that when heat is absorbed by the system at constant pressure, we are actually measuring changes in the enthalpy. What we are doing? We are measuring the changes in the enthalpy. Remember, delta H is equal to QP. Delta H is equal to QP. What is this QP? Heat is absorbed by the system at constant pressure. Heat is absorbed by the system at constant pressure. You can ask me, sir, what will be the value of delta H? Here can delta H be negative or positive or both? Yes. When delta H is negative, it will be for the exothermic reaction which evolve heat during the reaction, and when delta H is positive, it will be for endothermic reactions which absorb heat from the surrounding. You have to just remember when the heat will be evolved means taking out, that time delta H value will be negative, and when heat will involve means endothermic reaction, that time delta H value will be positive. And since it is for the constant volume, delta V is equal to 0, so that's why delta U is equal to QV. Internal energy is equal to QV. Therefore, you can write the equation called delta H is equal to delta U, that is also equal to QV. So what you have learned here, you have learned that the difference between the delta H and delta U is not usually significant for the system consisting of only solid and or liquids. Solids and liquids do not suffer any significant volume changes upon the heating. The differences, however, becomes significant when gases are involved. Let us consider a reaction involving the gas. If VA is the total volume of the gaseous reactants, VB will be the total volume of the gaseous product, NA is the number of moles of gaseous reactants, and NB is the number of moles of gaseous product. So all the constant pressure and the temperature by using the ideal gas equation. What is the ideal gas equation? Ideal gas equation is equal to PV is equal to nRT. So if we talk about the first volume, A volume, so PVA is equal to NART, and if we talk about PVB, that is equal to NBRT. Thus PVB minus PVA is equal to NBRT minus NART. That is also equal to NB minus NART. So PVB minus VA is equal to NB minus NA into RT. So P delta V is equal to delta NGRT. Here you can ask me what is delta NG? It refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. When you substitute the value of P delta V, so delta H is equal to delta U plus delta N GRT. So the equation is useful for calculating the enthalpy and internal energy, or vice versa, you can say. So as here you have just heard about the new state function term that was also known as enthalpy, denoted by capital H, how the changes of internal energy and the changes of volume and the changes of enthalpy. By substituting the value, you have got delta H is equal to delta U plus NGRT. What is this NGRT? It refers to the number of moles. Ng refers to the number of moles of the gaseous product. Ng refers to the number of moles of the gaseous product. You have to just remember this thing. Now we will move towards the new property called extensive and intensive properties.